All right, well, for today, I want to finish partial fractions. And I just want to recall first, because if I don't put this down again, I'm sorry, it's kind of long, then I think once you sleep on it, it's hard to pick it up again. Partial fraction said this: if uh, an expression that's a polynomial divided by a polynomial, where the degree in the bottom is higher, can be re-expressed as a sum of terms that correspond to the factors of the denominator only. It doesn't matter what the numerator is, it's the same form. It will change the constants that go in there, so it's not that it doesn't change, but the form will be the same. One, you put in for each factor in the denominator that's a linear factor, ax plus b. You write ax plus b to the k, each linear factor to the k. You write a constant over ax plus b plus a constant over ax plus b, where ax plus b is factored out of the denominator. You know that one, but these constants on top you're trying to figure out. Plus ak over ax plus b to the k. And the partial fractions theorem says that for each factor here, you have to write one of these things. If it's a factor of multiplicity k, you have k terms. Then for each factor, ax squared plus bx plus c to the k, irreducible. Remember what an irreducible quadratic is? Yeah, you can't factor it into linear factors without using I. So it's irreducible over the real numbers is what we say. And that happens when the discriminant is negative, right? Talked about that last time. B squared minus 4ac negative. So for each irreducible quadratic to the k, we write b1x plus c1 over that irreducible quadratic. A quadratic just means a second degree polynomial. That's why if quadratic equation is ax squared plus bx plus c equals 0, that's quadratic equals 0, quadratic equation, right? Plus dot, 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 and you write k terms here, bk x plus ck all over ax squared plus bx plus c to the kth power. So we didn't get to this one last time with the irreducible quadratics in it. We just did some of these. But you add all those together, and the partial fraction says every quotient of polynomials can be re-expressed by this method, and effectively what it does is it undoes the common denominator of that quotient of polynomials, depending on what the factors are of the denominator. So here's an example here. Suppose I had the integral of 39x squared over x plus 1, x squared plus 1. This is just like one of your homework problems. I've kept the numbers in here really simple. And what do I know about this one? This is hard to integrate by any of my other techniques. So what I'm going to do is use partial fractions. and rewrite the integrand just by this algebra, right? Let's get this. Partial fractions here says, well, this isn't ax plus b, this is this kind, and it's only to the first power, so I only have one term. So I'll write a number over x plus 1. This one, however, is an 1x squared plus 0x plus 1 is a quadratic, and it doesn't factor anymore, right? In fact, if you try to factor it, it factors as x plus I times x minus I. But if you compute the discriminant, b squared minus 4ac is negative 4, so you know it's going to factor with the imaginary unit in it somewhere. So this is going to, this one I can't factor into product of linear factors. I just have to do this method and say, well, it's b1x plus c1 over that irreducible quadratic x squared plus 1. And the partial fractions theorem guarantees me that there is some numbers a1, b1, and c1 for which this is so. In fact, they're unique always. I'm going to erase this. So what are they? The way you find those out is you either go to your calculator in the catalog and you choose the expand function. By the way, the calculator will do this integral for you too. Check your answer on the test if I give this. But on the test, I'm going to make you put in the steps that your calculator won't give you. So you have to do all these on the homework, right? But your calculator will do the integral. Also, it will do the partial fraction. So you can push expand and type out of the catalog. It will put in the word in the parenthesis. And then if you type by hand 39x caret 2 for x squared divided by key parenthesis x plus 1 divided by again, so it's divided by both, or you can put double parentheses and multiply. X caret, oh boy, I'm running out of room online there, divided by x caret 2 plus 1, close parenthesis, and then comma x parenthesis. So it tells you expand this expression in terms of x. It will tell you the partial fractions right there, and you can use that on the test if you want, right? You can use any calculator you want. Just, or you can do it by hand, right? You can multiply through and do it by hand. And what you do here is you multiply through by the denominator. You get 39x squared on the left equals x plus 1, x squared plus 1 times a1 over x plus 1, right? The denominator multiplying both sides multiplies this, and it multiplies this. Well, I'm going to run off the end here. Plus, let me move it over. So x plus 1, x squared plus 1 multiplying this one, plus x plus 1, x squared plus 1, multiplying the second one, b1x plus c1 over x squared plus 1. Turn that just a little. Oh, I'm on there, I guess. Yeah. All right. So it looks like that, and then the x squared plus 1 cancels the x squared plus 1. X plus 1 cancels the x plus 1. And what I've got is 39x squared equals a1x squared plus a1. And then I've FOIL this out also. X times b1x is b1x squared. X times c1, right? I'm multiplying this whole thing. Plus x times c1 plus x times b1 plus 1. Plus c1. So there it is. And now you group like terms and put 0 on one side. So now I've got something times x squared plus something times x plus the constant terms. And what multiplies x squared? Well, I've got a1x squared and I've got b1x squared. So I've got a1 plus b1. And I want to get 0 on the left, so I'm going to take this 39x squared and subtract 39x squared from both sides. So I'll get a minus 39 multiplying x squared over on the right also. Then the x terms, I've got c1x plus b1x, so I'll just put b1 plus c1. Then the constant terms, I've got a1 and c1. So satisfying this equation for all x not equal to -1 is equivalent to finding the partial fractions expression there. Now, if that's going to be 0 for all x, except x equals -1 where it's not defined, then it has to be that each coefficient of a power of x is 0. This must be 0, this must be 0, and this must be 0, right? Because after all, this is a quadratic equation. A number times x squared plus a number times x plus a number equals 0. It can only have 0, 1, or 2 solutions. It can't satisfy the equation on an interval. Any interval has an infinite number of x values. You can't make them all satisfy, only 0, 1, or 2 of them. Unless all the coefficients are 0, right? Then you can make it work, as this says 0 equals 0. And by the way, this works for higher degree polynomials. If you have more factors in the bottom so that you get like x to the fourth and x cubed and so forth, the coefficient of each power of x has to vanish. The fundamental theorem of algebra says, implies that you can, for an nth degree polynomial equals 0, you can have at most n distinct solutions. And so if you can only have n solutions for an nth degree polynomial, then still all the coefficients have to be 0. So you always set all the coefficients to 0 no matter how high a power you have here. Fundamental theorem of algebra tells you that there's at most n for an nth degree polynomial, not an infinite number. So now what we have is a system of equations equivalent to that, which says a1 plus b1 equals 39 for the first one to vanish. b1 plus c1 equals 0. And people like to write these in columns where the b's are here and the c's are here and the a's are here, just to keep from making mistakes. And then a1 plus c1 equals 0. Then you can perform elimination on this. Call these equations 1, 2, and 3. And this can be kind of tricky, but elimination, remember, you try and add multiples of certain equations to others to eliminate variables, right? So I can make an equation 4 here, for instance, by taking equation 2 minus equation 3, right? 2 minus 3. And why do I do that? Because if I do that, it'll be c1 minus c1 will cancel, and the c1s will go out. So I'll say 0 minus a1 is minus a1. b1 minus nothing is plus b1. c1 minus c1 is 0, and all has to add up to 0, right? And this always works, right? Because if these two sides are equal and these two sides are equal, and this plus this equals this plus this, right? So this is now, boy, I didn't get any fewer equations, but what I was trying to do here was getting an a1 and a b1 like in my first equation. There is an orderly algorithm by which you can make this always work called Gaussian elimination. The great Gauss was considered one of the 3 greatest mathematicians of all time. He lived in the late 18th and early 19th centuries, and he was probably the last mathematician who understood the whole field of mathematics of his day. He's brilliant. It was just amazing. There's funny stories, if you can read them in your book even. When he was 2, he found out corrected his father's payroll, I guess. Not corrected. He found his father making a mistake on the payroll and told him. And he said he could do some rudimentary numbers before he could speak and those kind of things. And so they put his picture on the Deutschmark in the early 20th century for a while. But so he is quite a guy, but he's got Gaussian elimination named after him, where there's an orderly algorithm. You can always eliminate the variables and find out the solution or show it has no solution to these systems of linear equations. So this is a system that can always be solved, and when it comes from partial fractions, it always has exactly one solution. In fact, you can prove that. We won't do it here. But so if you get no solution or an infinite number of solutions, you made a mistake somewhere, right? That's the point. But I'll add these down to get this equation, and I'm not following Gaussian elimination. I'm just doing general elimination, trying by hook or by crook to get rid of the variables. And I've done this. Now I can take these two that both have a1 and b1 in them and use these to eliminate one of those, and then I'll have just one variable left. So now I'll take equation 5 can be equation 1 plus equation 4, right? And now a1 plus minus a1 gives me nothing. b1 plus b1 gives me 2b1, and 39 plus 0 gives me 39. So that's what you do. You eliminate variables by adding multiples of some equations to another to get new equations and get it down to where you have one variable. Here we get b1 has to be 39 halves. Take a linear algebra class and they'll show you the nice algorithm to always get this. It's not that bad. It's pretty straightforward. It's easier than calculus, I think. And it's actually a very important course. Working in a lot of industry for years, the things I used a lot were the numerical methods in programming, where you had to program up a lot of things on the computer. Calculus and linear algebra, those three came up a lot, at least in the aerospace industry where I was. All right, so here's b1 equals 39 halves. Now you can back substitute. Put this into any one of the other equations. Like, let's put it into 2 and say b1 plus c1 is 0 now becomes 39 halves plus c1 equals 0. Tells me that c1 must be minus 39 halves. Moreover, I can put it into equation 1. Once I have b1 and c1, and here I've got a1 plus b1 is 39 halves equals 39. Well, that tells me that a1 is 39 halves. So I've got all three of these, and now I know exactly how to write this. All right, I'm going to take this thing that I wrote here and update it. Hence, having solved for those things, this is exactly equal to this with a1 equal 39 halves, b1 equal 39 halves, and c1 equal minus 39 halves. There it is. Which means my original integral, well, let's write it even easier here, 39 halves times 1 over x plus 1 plus x minus 1 over x squared plus 1. I'll factor out that 39 halves just for simplification purposes. And now my original integral becomes the integral of this. I can pull the 39 halves out and integrate 1 over x plus 1 plus x minus 1 over x squared plus 1 with respect to x. That good so far? So partial fractions is nothing more than algebra to rewrite a quotient of polynomials. Polynomial is a number times a whole power of x plus a number times a whole power of x plus dot 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 plus a plus a number, where the degree of the top has to be less than the degree of the bottom. And if you rewrite it over as quotients in terms of the factors of the denominator, linear terms ax plus b and irreducible quadratics ax squared plus bx plus c. And you can think of this one as 1x squared plus 0x plus 1, we said. And then each of these you can integrate by your previous technique. So 1 over x plus 1, I can integrate as 1. Well, let's write it out. Sometimes I do 2 steps at once. That's the hard step. I'm going to rewrite this. X over x squared plus 1, I'll put in its own integral. And minus 1 over x squared plus 1, I'll put in its own integral. Why would I do that? That's how you want to integrate these. What happens is you have to break this up into 2 pieces. What you want on here is the derivative of the bottom. Since the derivative of the bottom is 2x dx, I'd like to have 2x dx here or a multiple of it. So this is 1/2 of the derivative of the bottom. And then what you do is you put the derivative, some multiple of the derivative of the bottom here, and then whatever's left over, in this case minus 1 here. Now what you can do is do this one with a u substitution. If the top is the derivative of the bottom or a multiple thereof, you can let u equal the bottom, x squared plus 1, and du will just be a multiple of the top. In this case, du is 2x dx. So multiplying by a half du can replace the x dx that you see, right? So now this will be a half du, and this will be u on the bottom. I get integral 1/2 over u. I can do that. This one over here, if I have 1 over a linear factor, I let v be the linear factor, v equal x plus 1. Then dv is the derivative of that dx. In this case, it's just 1 dx, right? Let me know if this is too hard to see in the back. It's a long ways in this classroom. Is that sort of visible or is that hard? Are you okay? Okay. I'm going to try not to write quite that small. I'm just realizing. All right, I've got 39 halves times integral 1 over v dv plus integral 1/2 du over u minus integral 1 over x squared plus 1 dx. Now this one here, right, this is just natural log absolute value of v plus a constant. This one here, the 1/2 comes out, and then you've got natural log absolute value of u. And then over here, remember what this one is? You need this one for this assignment. Yeah, arctangent. Derivative of arctangent was 1 over x squared plus 1, so the integral 1 over x squared plus 1 is arctangent. Yeah, you have to memorize that one for this section. And then there's plus c when I remove my last integral, right? So I've got 39 halves times all of this. And I got to put back what u and v are. So it's 39 halves. ln v is ln of x plus 1 absolute value plus 1/2 ln absolute value of x squared plus 1 minus arctangent x plus c. And I'll give you another hint on the homework pickiness. Somebody told me, I haven't tried it, that if you leave this absolute value on here, it will throw you an error. Yeah, it'll throw you an error. Drop the absolute value. X squared plus 1 is all positive, always positive, so you don't need the absolute value, right? But achieve, I think, will mark it wrong, and you'll never know why if you leave the absolute value on there. So take that off when you can. Yeah. It works like that? Oh, okay. Yeah. Okay, so I guess you can put the absolute value inside then. Okay. So there's that one. Thank you. All right, well, the next one illustrates the next difficulty. That's how you deal with the irreducible quadratics. You break them up into two integrals. One of them has the derivative of the bottom on top, and the one of them has whatever's left over. Then there's this kind of integral. X cubed plus 4 over x squared plus 1. I'll pick a similar denominator. How about that one? This one I can't do partial fractions immediately. Why not? Yeah, I need the denominator of the bottom to be higher degree than the top. This is degree 2 on the bottom, since the second power is the highest. This is degree 3 on the top, since third power is the highest. So I have to get the degree of the numerator less. What I can do is called polynomial division. I'll divide the top, x cubed plus 4, leave some space in here, by the bottom, x squared plus 1. Polynomial long division is just about like long division with whole numbers. Maybe I better put it over here. So similar to, suppose I wanted to divide two whole numbers. I want to divide 117 by 4. What could I do? I can do the division algorithm for whole numbers. 4 into 117. I'll say, well, how many 10s times 4 goes into there? 10 times 4 is 40, 20 times 4 is 80, 30 times 4 is 120 is too big. So I can take 20 times 4 and put it in. 20 times 4 is 80, and I put that here and I subtract it down. I'm left with 37, right? Now, how many units times 4 goes in there? 9 times 4 is 36. So I put plus 9. 9 times 4 gives me 36, and then I've got a remainder of 1, right? So this is my remainder, and this is my quotient, 29. This is my divisor. That says I can rewrite 117 over 4 as the quotient 29 plus the remainder 1 divided by the divisor 4, right? We're going to do the same thing with polynomials. We're going to say if I want to divide this polynomial into this one, how many times does x squared go into x cubed? It goes in x times, right? And so I'll take this, just like I took this times this and put it down here, I'll take this times this and put it down here. X times x squared gives me x cubed. X times 1 gives me x. And that's it. Now I subtract down just like I subtracted down here, right? X cubed minus x cubed is nothing. No x squared terms. 0 minus x is minus x, and 4 minus nothing is 4. So you subtract the bottom line from the first. No, because that's the top line. Top line minus the bottom line. And now I say, how many times does x squared plus 1 go into x? Well, now, once this is lower power, you stop. So this is lower power, lower degree. Stop. That's polynomial division. It tells you that this quotient that you have here, x cubed, I'll put 3 dots. That means therefore in mathematics. Therefore, x cubed plus 4 over x squared plus 1 by the division algorithm for polynomials is the quotient x plus the remainder minus x plus 4 over the divisor x squared plus 1. This is completely equivalent to that, right? Just like when you do the fractions. That's how I'm going to do this one, because now this will be lower degree than this one. I can apply partial fractions, right? So that always works. It doesn't matter if you get a higher degree on top. You just have to do a polynomial division like that and then partial fractions. All right, so hence we'll say the integral x cubed plus 4 over x squared plus 1 is rewritten after polynomial division as integral x plus minus x plus 4 over x squared plus 1. And now I'd like to use partial fractions on this, but I actually don't even need to. It's already done, right? It's an irreducible quadratic in the bottom. So we're done, right? B squared minus 4ac is negative 4 here. It's already done. So we can integrate it like it is. And what we do is we say this is the integral of x plus, or let's say minus, integral of x over x squared plus 1 plus integral 4 over x squared plus 1. And I do this in the same way as in the last problem. Here, this should be a derivative of the bottom times dx, and it is, right? It's 1/2 the derivative of the bottom. If I had x squared plus x plus 1, I'd have to have, like, x plus 1/2 here. So I'd have to keep part of this constant in here, so to make the top the derivative of the bottom. I picked a particularly simple problem here. All right, so the top is now derivative of the bottom. I can substitute u equal x squared plus 1. Then du will be its derivative dx is 2x dx. And to substitute for x dx, I just put 1/2 du, right? So scratch this out, put 1/2 du. Scratch this out and put u. And this integral becomes 1/2 integral 1 over u du. This one, if I pull the 4 out, it's integral 1 over x squared plus 1 is arctangent again. What happens if I have 1 over x squared plus 4? What can I do? You can make that substitution since this is an x squared plus a squared. X equals 2 tangent theta. But what's even easier is just to let 4u squared equals x squared. So it must be that 2u equals x. Make a substitution, 2u equals x. Then you'll get 4u squared plus 4, and you can make this into an integral 1 over u squared plus 1. So you can do it that way. If you get a x squared plus an a squared, just make this kind of substitution, and then it becomes an arctangent, 1 over u squared plus 1 times 1. Since it's not that way here, we won't do that, but I'll just point out if it's x squared plus a number squared, you can still deal with it like that. All right, and then integral of x gives me x squared over 2. There we go. Integral 1 over u is natural log absolute value of u. And u was x squared plus 1, and so I can leave off the absolute values. There it is. Okay. There's what you do if the degree of the top is at least as big as the degree of the bottom. Let's try one more here. Another thing that can happen is once in a while, you'll get an integral that turns into one of these. I told you I had that big book as a graduate student. I think I told you, of integrals, so I could do my classes because I get terrible integrals, and you just had to have the right clever substitution. So you'd look up what somebody else did. I had a friend's an engineer. He said, "What you do when you don't know how to solve a problem, you go ask somebody else who's done it." And I said, "Oh, it's a good strategy, you know." But here's this one, similar to a homework problem. If I want to integrate secant squared theta over tangent squared theta minus 289 with respect to theta. How about that? That looks initially hard. Part of this is just to get you a little practice at these so you can look at them and recognize what to do. And here's a hint. We said on the u substitution, the primary thing is if you see a function of a function, think what would happen if you let u be the inside function, right? Sometimes you're lucky and you get du out here. Another thing that can happen is if you see something multiplying, like in this case, a function of theta multiplying d theta, you might think, what has this derivative? Maybe if I make that substitution, let's let u equal, what has this derivative? Tangent has that derivative. So I'm going to think, what if I let u equals tangent theta? Then this will be du, right? Du will be the derivative of tangent theta, secant squared theta d theta. So that's the other trick. If you see something multiplying d theta, think, what's its integral? I can let u be that. Maybe it'll make it easier. Maybe it won't. That's the trouble with the u substitution. And then the trouble is there's all sorts of clever substitutions that are hard to guess. That's what the trigonometric substitutions were all about. You didn't have a function of a function or this necessarily, but you figured out a clever substitution anyway. So that's why you have the books of those. And now it's all online. You just go to the calculator online. You don't need my big book anymore. It's like, you ever been to the used bookstore? You see those tables of 5-place logarithms. You know, you can do all those on your calculator, but many years ago, before calculators, you got something from the 1960s. They looked those things up in books or used a slide rule or something. All right. So now I'm going to substitute that for u, and then if u is tangent theta, this is u squared. Converse this into integral 1 over u squared minus, and I'll write 289 suggestively as 17 squared du. Now that must convert to something. What could that be? And I'll give you a hint. You could actually use your inverse hyperbolic trig functions here. However, since this is in the other section, I wouldn't guarantee Achieve is going to tell you the answer is correct. I might give this to you in a test and say use inverse hyperbolic trig, since if you're doing it in your calculator, give it another form probably. But this can be done with partial fractions too. So some of these can be done either way. And we can think of this one as integral 1 over u plus 17 times u minus 17 du, right? And now I recognize it's a polynomial of degree 0 over a polynomial of degree 2, right? So I can apply partial fractions to this. For that, I need to factor the bottom and figure out what's the factor. How does that factor? Well, 1 over u plus 17 u minus 17 has to be equal, right? This is a first power and this is a first power, so there's just one term for each. A1 over u plus 17 plus A2 over u minus 17. I multiply through by u plus 17 times u minus 17. I got 1 on the left equals A1 times u minus 17. The u plus 17s cancel. Plus A2 times u plus 17. The u minus 17 is canceling. So you start to do these faster. You just say multiply through by u plus 17, u minus 17. Everything cancels but this. Everything cancels but this. And now you can group like terms again. You need to subtract the 1 over the other side to get 0 over here. And you've got terms multiplying u, and you've got constant terms. Let's see, a1u plus a2u. So I've got a1 plus a2u. Then I've got a1 times minus 17 plus a2 times plus 17 minus 1 that I subtract over. There we go. Okay. So this one, you made a substitution and then you got partial fractions is the idea. So this says a1 plus a2 equals 0. From the first part, right? Each coefficient has to vanish. And this one says minus 17a1 plus 17a2 has to equal 1, so that this minus 1 equals 0. Right? Well, I can use elimination again, right? If I call this 1 and 2, now I'll add 17 times equation 1 to equation 2. 17a1 plus minus 17a1 cancels, and I get nothing. So I picked the right multiples to make a1 go away. Now I've got 17 times a2 plus 17a2 is 34a2 equals 17 times 0 plus 1 is 1. Evidently, a2 equals 1/34. There we go. Then put it into either equation. First one looks easier. And I'll get a1 plus 1/34 equals 0. So a1 must be minus 1/34. Finally, my integral is then integral of a1 over u plus 17 plus a2 over u minus 17. All right, we took this and rewrote it like that, where a1 was minus 1/34 and a2 was plus 1/34. All right, so each of these is easy to do, right? This is, if you make a substitution, v equals u plus 17, and this one, w equals u minus 17. Then dw is du, right? Derivative du is 1 du. dv is du here, and this becomes minus 1/34. The constant comes out, integral 1 over v. This one becomes plus 1/34, integral 1 over w. So we'll rewrite this as minus 1/34 natural log absolute value of v plus 1/34 natural log of absolute value of w plus a constant. And then v was u plus 17. And u was